Hello, welcome to Weather Lab walkthrough for Lab 1, Vertical Structure of the Atmosphere. You should be following along with your lab book, so if these images are not clear enough to read, that's okay because you have your lab book with you, so you're looking at your lab book and using my images seen here as a reference. And yes, you're going to always need volume. I'm never going to type out what I'm saying or give you that sort of setup, but you can turn on closed captioning and see what I'm saying that way, so that is an option as well. So first things first, you're going to begin by reading through the paragraphs that are written before you start the lab, and it's going to start talking about vertical structure of the atmosphere and how as you go up in the atmosphere, the density and the pressure decreases as you increase in altitude. And there's a general understanding, and one of the key pieces that you should pick up right away is that there is this little sentence right here on the far side: for every 5.6 kilometers you ascend, so every 5.6 kilometers that you go up in altitude, there is half the air mass above you. So every 5.6 K, you will have half the amount of the atmosphere that you had previously. So that brings us down to question 1 at the base, which says, using the above rule, the one we just highlighted, indicate the percentage of atmosphere above each height in table 1. So now that brings me to my second page, which I have as an image here, with this nice little table. And we start out right away with sea level, and we know at sea level, which is basically where we live, the atmosphere will be 100%. And we know every 5.6 kilometers, it will be half of what it was. So at 5.6 kilometers, the atmosphere will be 50%, which means at 11.2, it would be 25%. And at 16.8, it will be 12.5%. And at 22.4, it will be 6.25. It's not letting me write this far up on my image. I apologize. 6.25%. So there we go. Nice. Now that we know that, we can move on to question 2. Okay, so for question 2, you're going to be creating a graph of the table, and you're going to label your axis. So your y-axis is going to be the kilometers of height, and your x-axis will be your percentage for the amount of air molecules present. And we're going to label them up, and I would suggest going by tens on the x-axis. So this would be 0, and this would be 10%, 20%, 30%, 40%, 50%. Make yours look very clean: 60, 70, 80, 90, 100. I'm writing with my finger on an iPad, so mine is not going to be nice and neat. I expect yours to be. For the kilometers, on the y-axis, I'd go by 2s. So this is going to be 2 kilometers, 4, 6, 8, 10, 12, 14, so on. Finish labeling it out. So now I'm going to mark my points on the x-axis, and the first point I'm going to mark is my sea level, which is 0 kilometers, and it's going to be 100%. That'll be my first dot on my image. I'm going to change color to try to help make it readable. So my first dot, 0, 100%. My next dot will be at 5.6 kilometers, and it will be 50%. So 5.6 is going to be kind of halfway in between, and it's going to be here. My next dot will be at 11.2 kilometers, and it's going to be 25%. So between 25 and 30, and 11.2, so it's somewhere in there. Next one at 12.5, which is going to be a little closer to 10, and that's at 16.8 kilometers. So that's kind of like here. Whoop! Come on, stylus, work for me. right there. And then finally, 22.4, which I got squishy on the top of my y-axis. Just be careful when you're writing. You guys can do this cleanly. Will be the 6.5 kilometers. When I go to draw my line in, I'll get this handy dandy little curve. This curve is called atmospheric standard. This is the known understanding of what we expect the atmosphere to be like at any given altitude. Actually, we know when there's something that's disturbing normal weather conditions by changes in atmospheric standard. So this is the understood norm. So one way that you could figure out at what altitude you could expect a certain percentage of air molecules is to look it up on a graph. But if you're at a specific height and things are more confusing, the next stage is to look at page 3, and that is to work with an equation to find out how much millibars of pressure, air molecule presence you can expect. So page 3, question 3 just tells you to label your graph, which I told you to do in the first place, but please make sure you label it. I will take points if you missed that. Moving forward, it then explains that if you need to find the amount of air molecules at a given altitude, you can use this equation here, and you will solve for x being the height in kilometers that you're at. So for the example that they give you, they use Everest, and they say Everest is 8.85 kilometers. You place that in the x, and you divide that by 5.6. Then you will remember that number and clear out your calculator and put in 0.5 to the power of that number, which should be 1.58. Oh, it's in the book. I didn't even notice it's right here. That's me. I'm looking away. 1.58. And then you will times that by 1,000 millibars. Your final answer will be the amount of air molecules, and this is why we talk about needing breathing assistance. If you hike at really high altitudes like Everest, you would carry breathing machines to make sure that you're safe, and also talking about acclimation and altitude sickness. This is all a part of lack of air molecules. You literally have less oxygen molecules to breathe. So that's how you do that. So now you're going to practice doing that, and they give you some different altitudes. They're going to give you a cruising jet. They're going to give you Pikes Peak's altitude, and then they show you the surface, which is dorky down here. They give you the answer to that. So you're going to practice using the equation, and then moving forward, once you're done doing that, so pause the video and meet me back, and we'll talk about question 5. So now question 5 is going to start to ask you to look at finding certain amounts of air molecules. So specifically looking for the amount of nitrogen or oxygen in the atmosphere. So that means we're going to alter the equation a little bit. And right away they give you some facts. Right here they tell you the atmosphere, and they give you an example. It says nitrogen gas is 78% of the atmosphere, which means that out of that 1,000 millibars that we were working in the previous equation, 780 of them are nitrogen. Oxygen, at the other hand, is 21% of the atmosphere, which means 210 of them will be oxygen. So, if they ask you to find the partial pressure of oxygen at sea level, the answer is 210 millibars. So we answered 5 together. Now we're going to make this a little bit more tricky and go down to question 6, where they're going to ask you for the partial pressure at the altitudes that you previously answered for. Pikes Peak, which you know from the previous question, is 4.34, and this is kilometers, and the altitude of Everest at 8.85 km. Now because you're doing oxygen, the equation will change. The new equation that you're going to be working with will change that 1,000 millibars to 210 millibars, and this will allow us to solve for oxygen. So you're going to be plugging in your altitudes at x and you're going to do them. So for the first one, you're going to do 4.34 divided by 5.6. Do that to the power. So it's 0.5 to the power of, and then times that by 210 millibars. And for the second one, you're going to do it to Everest. So your X will be the 8.85. And this will allow you to have the oxygen readings. Now, the percentage will stay the same. So whatever your percentage was in the previous, this is still the same percentage, because your total was 100% oxygen was 210 millibars. I do hope this all helps you, and I might continue with more video, or we might call it good for the day. So this is basically a part 1 potentially.